Okay, folks, dot products. We have two vectors here. We're going to do a dot product. A dot product, shockingly enough, is a big old dot. Now, we have 3 times 2. That we use in multiplication. We use a small dot. This dot product is going to be similar to multiplication, but somewhat different. In essence, what we're going to be doing is we're going to be taking what would be the product that ends up in the middle of a FOIL. So we have x squared plus 3x plus 5x plus 15. It's this piece here in the middle where we cross this variable with this constant that makes the portion in the middle. And since you get 2 of them, a 3x and a 5x, and add them together, this portion here is what we're going to go with, and it's the dot product. Now, between two vectors, big dot, 6 comma negative 3, we're going to simply do the following. We're going to say 4 times 6 plus 5 times negative 3. Put those together, 24 plus negative 15. The answer is 9. That is the dot product. The dot product is used for a number of things. First, we can find the length of a vector, and previously we talked about how you just do a squared plus, or ax squared plus ay squared. That is also true. It's also a dot product because what you have is a dot a. If you in essence square itself, that is also the distance. So these two pieces are equivalent, where you take each piece and square, or you take a dot itself. Well, it kind of makes sense that if I have 4 comma 5 dot 4 comma 5, that it's going to be 4 times 4 plus 5 times 5. Well, wait a minute, that is the dot product. Square root the whole thing, so I get 16 plus 25 is 41. I end up with square root of 41. That's the length of the vector from 4 to 5. That is one use. The second use is for determining if two vectors are perpendicular. Now let's see here. If we have a vector 2 comma 3 and the vector negative 3 comma 2. Let's see if these two vectors are indeed perpendicular. Do they meet at a right angle? Now, to do that, we're going to simply say this bit here, 2 times negative 3 plus 3 times 2. And I get negative 6 plus 6, and indeed we get 0. Now you say, well, that kind of makes sense. You'll notice if I were to graph these, I come up with 1, 2, and 1, 2, 3. The other vector, if I happen to start from the same spot, and I go back 1, 2, 3, and I go up 1, 2, it does look as if it should make a right angle. Now, I, of course, cheated by making the vectors negative reciprocals of one another, but the key here is they should meet at a right angle. And it doesn't matter what angle that orientation that angle has, they're still going to be perpendicular to one another. Use number 3 has to do with two vectors. Again, let's use our vectors here. Let's use 4 comma 5 and 6 comma negative 3. I want to know, are those perpendicular? Well, we did the dot product, and the dot product from the previous, which was a dot b, was 9. Now, if I were to get a dot product of 0, these two vectors would be perpendicular. Since this dot product is 9, we know it is not perpendicular. So, the question becomes, what angle is between the two vectors? To find the angles between the two vectors, we need to use the following formula. cosine theta equals A dot B over absolute value A, absolute value B. Now the absolute value is magnitude, just like the absolute value of -2 has a magnitude of 2. Same idea. Absolute value means magnitude. So if I do this, I say cosine theta equals A dot B. Well, I came up with 9 for that. And I need the magnitude of A. Well, the magnitude of A happened to be square root of 41. And so now I need the magnitude of B. Well, I can do that using my use number 2. 6 squared plus -3, the quantity squared. Come up with 36 and 9. That's 45, root 45. So I have the cosine of theta equals 9 over root 41 times root 45. The question becomes, what is that angle? Through the magic of television, we come up with 77.9 degrees. That is the measurement between those two vectors. Now, if you remember back when we had to put the vectors head to tail, find the resultant, get the angle in between the two vectors, well, that was when we were putting them head to tail. In this case, the angle happens to be when they are tail to tail. So we do need to be careful of the distinction between the two. So we have yet another use for dot products. We have one more to go. One more use for our dot product to go. And if I have two vectors, got my 4, 5 and my 6, -3, let's put them on a graph. In fact, we'll put them on a fresh graph. One, 2, 3, 4. 1, 2, 3, 4, 5. There's one vector. That's A. Now we have 6, -3. 1, 2, 3, 4, 5, 6. 1, 2, 3. And we have this vector down here. Now, if we were to look only at vector B, it obviously goes from here to here. But because A is also pushing, yes, it's pushing this way, but it's also pushing somewhat in the same direction as B, the question becomes, how much of A affects the movement in B? How much added motion, how much added force does A give to B? Well, if we were to drop a line perpendicular, this would be the vertical component of A, and this would be the horizontal component of A. Now, it's not truly horizontal because it's not oriented on an x-axis, but it's the portion of the vector that goes with B. To find that, we need to do what's called a projection. And in this case, it's the projection, J, not G, of A onto B. And to do that, we're going to take A dot B all over B's magnitude squared times vector B. So, let's do A dot B. Well, A dot B was 9. We had the magnitude of B, which was square root of 45. That is squared. And that value we're going to multiply times vector B, which was 6, -3. So the question becomes, how much is the projection of A onto B? It's going to be found using these values right here.